Hello, everybody. My name is Bryce Adelstein-Lallbach. I work at NVIDIA, where I am the CUDA C++ Core Libraries lead. I am also a member of the C++ Standards Committee. I chair the Library Evolution Incubator group, and relevant to this talk, I chair the Tooling Study Group, although I am not a tool vendor nor a compiler person. So today, we're going to be talking about C++20 modules, which I believe is the most important and biggest feature coming in C++20. But first, I want to talk about something that I think is more important. Before you can solve a problem, you have to recognize that you have one. So as a leader in the C++ community, I want to publicly acknowledge that C++ has a diversity problem. Include C++ is a group of C++ programmers who are working on solving that problem. And if you're interested in learning more about Include C++ or diversity in C++ in general, you can go to our website, which should have been on this slide. It's includecpp.org. We also have a Discord server. You can get yourself one of those T-shirts or sweaters that you see at all the C++ conferences. All right, so today we are going to talk about modules. So I'm going to start off by giving you a high-level, level of explanation of what modules are, and then I'm going to show you one example before I dive too much into why we want modules. I just feel like talks really should start with an example. So modules are a new compilation model for C++. And that phrase is actually a little bit hard to dissect, because a lot of us don't think much about the compilation model for C++ because it's been around for a long time, and it's just sort of something that we take for granted. Modules also give us a new way to organize and distribute C++ projects. Okay, so here's this little example that I promised. So on the left here, we have an example, a pre-modules example. In that pre-modules world, I'm going to call it throughout this talk textual inclusion. That is the model by which we build our programs today. So in this little example, I've got one header, math.hpp, that declares a function square that just squares an int. Then I've got a source file, math.cpp, that includes the header and defines the function that was declared in the header. And then in another source file, I have main.cpp. I include math.hpp, and I use the function that we defined. So we have two different source files here, two different translation units here, one that defines a thing, the other one that uses the thing. In the modular world, this example looks like this. So instead of a header file, we have a module interface unit. It's that .cppm file here. And it does the same thing that the header does. It declares the function square. It also exports it. We'll talk more about that later. And then we have a module implementation unit, which is just a C++ source file that has a module declaration in it. And that has the definition of square. And then again, we have the other source file that is going to use the function we defined. And it's, in this case, instead of including the header that has the declaration, it's going to import the module. Okay. So I'm going to make the bold claim that modules will have a greater impact than any other feature added after C++ 98. And what I mean by that is that modules will affect more things than any other feature that's been added post C++ 98. It will have a big and disruptive effect on our ecosystem. So let's look at how some other changes have affected the C++ ecosystem. For example, let's look at a library feature from C++ 11, std_thread. So std_thread is a library feature. It doesn't change anything about the language itself or anything core or fundamental to the language. It does actually have some language support in the execution model, but let's just think of it as a library abstraction for now. So this changed how C++ code is written, like how you actually wrote your projects. But now let's look at another change. Let's look at lambdas. So this was a language feature introduced in C++ 11. And of course, this changed how code was written as well. But it didn't just change how C++ code is written. It changed how C++ code is parsed. And so that means that it affected a lot of things that you might not think of. For example, IDEs, syntax highlighting, static analysis, documentation parsing All of these things, all of these tools that have to consume C++ code, they had to adapt to all of the language features in C++11 that added new syntax. So modules change how C++ code is written. They do change how C++ code is parsed, the syntax of C++, which is going to affect IDEs, syntax highlighting, static analysis, documentation parsing, etc., any sort of tools. They change how C++ projects are compiled, which means that modules will change build systems, continuous integration, anything like that. They change how C++ projects are organized and structured, which means that it affects how you package your libraries and how you distribute your code and your libraries to users. And it changes the way in which C++ projects are consumed. This affects all of your dependencies. It affects any other languages that want to interface to C++. IDEs, syntax highlighting, any sort of tools that need to be able to consume your project as a whole project too. The footprint of modules on the ecosystem is very large, and that's why I claim that modules will have a greater impact than any other feature added post C++ 98. And we all need to prepare for that new world. It will not be an overnight transition. It will be a long, perhaps decades-long process. All right, so we're going to start off this talk talking about the compilation model that we have today so that we can understand why we want something new and what's wrong with what we have. So what is C++'s compilation model today? How do we organize C++ projects today? And actually, let's ask a more fundamental question. What is a C++ program? What is C++? So when in doubt, often we look to the standard. So the standard says the text of the program is kept in units called source files in this international standard. Okay, so programs have some textual representation. It is stored in source files. A source file, together with all the headers and source files included via preprocessor directives, is called a translation unit. Okay, so we take source files, we expand any includes, and then that's called a translation unit. And then we take translation units and we compile them, and then eventually we combine them into programs. Okay, so pre-C++ 20, we had one type of translation unit, the non-modular unit. Now, we didn't call it the non-modular unit, of course, because we didn't have modules. We just called them translation units. But I will call them throughout the talk non-modular units. So this was, your .cpp files, which would include things. Those includes would get expanded, and they would get compiled into object files. All right, so what's a program? Well, the standard tells us that a program consists of one or more translation units linked together. It doesn't explain what linked together is. It's just sort of a term of art in the standard. So previously translated translation units can be preserved individually or in libraries. So the standard says, okay, you don't have to take all of the translation units and actually put them into the program. Some of them might exist in a library that you link against. Now let's walk ourselves through an example of the compilation, of the textual inclusion compilation model. Okay, so in this example, we are going to have two source files, a.cpp and b.cpp. Each one of these source files has its own header that declares things that are defined in that source file. Then we've got a third header, c.hpp, that just has some header-only utilities. It doesn't have any source file that defines anything. Everything is just defined inline in that header. And then we've got lib.hpp, which is the header to some library that we're going to link against because b.cpp needs some stuff from it. And you'll notice some interesting things here, like this file includes B and then C. This one includes C and then B, which has a is semantically different in the textual inclusion model. So the first thing that we do when compiling this code is we preprocess it. And as we said before, what preprocessing means is we take all of the includes and we textually expand them into the source file, and that produces a translation unit. You will notice that the boxes here have gotten larger because the actual thing has gotten larger. We've textually taken all those headers and we've just copied them into the source file and then called it a translation unit. So then next, what we do is we take these translation units and we compile them into some sort of artifact, typically called object files. And that gives us these object files. And then next, we link the object files together. So there are three steps in the textual inclusion compilation model. We preprocess, we compile, and then we link. Okay, so what's wrong with this model? why did we spend all this effort standardizing modules? So there's 5 main problems with the textual inclusion model. The first is that it is slow to compile. I don't think this will come as a surprise to any C++ programmers, but C++ is not known for fast compilation times. So textual inclusion means that we often parse and compile the same code multiple times during a build. In this example that we looked at before, we're compiling b.hpp and c.hpp twice, once in each one of the translation units, because we've textually included them into that translation unit. And lib.hpp was compiled once by us and probably once by whoever built that library for us. And this isn't just a cost at compile time. It's also a cost at link time, because we have to pay a tax at link time because the linker has to go through and merge any symbols that appear in both TUs. That's not cheap, and that can't be parallelized. And this gets much worse at scale. For example, if I have 7 source files that include 3 headers, I will end up compiling each header 7 times. There are some upsides to this model, namely that we can compile each one of these source files independent of all the other source files. It's embarrassingly parallel. It's very easy to parallelize. The problem, though, is that it's not very efficient. All right, the second issue is ODR violations. So ODR stands for the one definition rule. It essentially states that there cannot be more than one definition of an entity in a program. But the issue is that if you violate the ODR rule, your program is ill-formed, no diagnostic required. That is a nice way of the compiler saying, it's your problem, something will happen, we make no guarantees about what. The implementation is not required to reject your program. It's not even required to give you a warning. This is kind of like a compiler UB. In some cases, it might be a compiler error. In some cases, it might be a link error. In some cases, it might not be an error. It might work fine. And in some cases, it might be a runtime error. Let's look at an example of that. Suppose we have a header that defines a data structure tree node. And that data structure has an extra member when the macro debug is defined. If we compile one TU with debug defined and another with debug not defined, and then we link them together, we have an ODR violation. Our program is ill-formed, but no diagnostic is required. If we never pass a tree node between these TUs, then this program will probably happen to work. It's still ill-formed, but it'll probably be fine. But if we do pass one of these tree nodes between the TU boundary here, we're going to have a problem, because in one of these TUs, it thinks that the tree node is smaller than the other one, and they both disagree on the very layout of this type. So your code's going to blow up, probably. Okay, so the next problem is a lack of encapsulation. I'm going to argue that this is the worst grievance that we should have with the textual inclusion model. Headers do not provide us with a good way to hide implementation details. We can make members of classes private, but we cannot do that with types or variables or entire classes that are at a file scope. If you ship something in a header, people will eventually use and depend on it. Like, this is a very Hiram's Law thing. If you put it in your header, even if you claim that it is an implementation detail, somebody eventually will try to use it. So this leads people who write libraries to take defensive actions to protect their names in their libraries, such as using detail namespaces or uglifying names. The textual inclusion model also does not prohibit you from creating cyclic dependencies, which is unfortunate because cyclic dependencies are bad structural design, and we should have a system that forces us to avoid them. So in the textual inclusion world, this example here, which has a cyclic dependency, is code that's valid and fine and it'll compile. And this example isn't particularly malicious right here. We're using some forward declarations, and we happen to have an include cycle. But like, this will work. But when you run into cyclic dependencies at scale, it can often make it very difficult to restructure or reorganize code. I'm sure many of us have encountered this. So what we really want is a model where circular dependencies, which are structurally unsound and undesirable, are prohibited at compile time with a diagnostic whenever possible. Finally, textual inclusion is order dependent. So the order that you include things in matters. So let's look at an example here. We've got one header file that defines a struct S. We have another header file B that has a function foo that uses an S. And then we have a C, another source file here that includes A and then includes B. Now this will be fine because we happen to include A, which defines the thing that we use in B, before we included B. But if somewhere else in the code we invert the order of the includes, then we're going to have a compilation error. The issue here is that b.hpp has a dependency on a.hpp, but it's not been enforced that that dependency be programmatically in the code. And we don't want that. Dependencies should be explicit, not implicit. Okay, so now we're going to talk, this talk sort of breaks down into two parts. It breaks down into the using modules part, which is mostly about like import, and then the writing modules part, which is mostly about export. So what is import? Import is a new keyword in C++20. It imports a module and makes the exposed interface of that module available to you. So it is the modular world's equivalent of include. Before we go any further, though, I want to take a look at an example of the modular compilation model. So this is the same example that we saw before, just translated into modules. So let's start off with what used to be headers here. So now in the modular world, we've turned those headers into module interface units.cppms. And these are, they're very similar to headers. They essentially, they are files that describe the entities that are exported from a module, and they may have some inline definitions of entities that are in that module. So they're very similar to headers, but unlike a header, they are translation units. This is a very fundamental thing to understand about the modular inclusion model. In the modular inclusion model, or modular import model, interfaces are translation units. In the textual inclusion model, interfaces are not translation units. Interfaces are expanded into translation units. Okay, so then we have what were just regular source file, just regular translation units in the previous example. A.cpp and B.cpp. And now in this example, we've made them module implementation units. Module implementation units contain definitions of the private parts of modules. They are another type of new translation unit, although they don't have a special extension. They're just like your .cpps in the textual inclusion world. And of course, we still have that CPPM module interface unit, which does not have a corresponding implementation unit. That's fine. In the modular world, you can still have what is the moral equivalent of a header-only library. So this just has definitions of things in it. It doesn't declare anything that's not defined in that module. Okay, so the first thing we have to do when compiling in the modular world is we need to pre-compile module interface units into what we call built module interfaces, which is, you can think of it as like a serialized form of your compiler's AST. Those built module interfaces are going to, or you can think of it like pre-compiled headers. Those are going to be used by any other translation units that need to consume that module. So pre-compilation is a new phase of compilation. And importantly, the other phases of compilation have dependencies on these outputs here, which complicates the C++ compilation model a little bit. All right, then the next step is we go through the rest of the compilation process that we are familiar with. After we've precompiled the module interface units to built module units, or BMIs, we begin pre-processing. Now, note that we're not including any of the headers here, so we don't we're not including any of these interface units into the two implementation units here. So we're not textually expanding them into those implementation units. Instead, because they are their own translation units, we are compiling them as well. So then, after we've pre-processed, we move on to the compilation step here, where we take all of the translation units, both the interfaces and the implementation units, and we translate them into object files. Now note that lib.cppm has disappeared here. The reason for that is because that was an interface unit that we were using to some library. So that library, when that library was compiled, it compiled the it compiled the interface unit into an object file and linked it into that library. But it might have provided us with a BMI that we could have used, but let's just assume in this case that it didn't provide us with a BMI, because that's what we should assume in the general case, that BMIs can be distributed as an optimization, but typically, they can be distributed as an optimization, but you will always have the module interface source available. So we needed to build the interface unit so that we could use it in our build, but we don't need to actually build the object file for it because that was built when the library was built. Okay, so we are going to compile all of the translation units here. We've got 5 of them into object files. And then finally, we link all those object files together and link them against the library. And that produces the final executable here. So the major distinction between this model and the textual inclusion model, or there's 2 major distinctions between this model and the textual inclusion model. The first is that we needed to compile our interfaces because our interfaces are translation units. And the second is we had to do this pre-compilation step to build these BMIs that were going to be used in the compilation step to import in things from other translation units. So as we mentioned before, the textual inclusion model has the pro of being embarrassingly parallel, but the downside of not being very efficient because it textually includes the files into each one of the translation units that uses them. Now, the modular inclusion model is more efficient because the interfaces are precompiled just once instead of 7 times in this example, but it's not embarrassingly parallel because before you can start building all 7 of those source files that are using those interfaces, you need to have built the interfaces, which means that you need to have agreed on which threads or processes are going to build those interface units. You can't just spawn off and have everybody work independently. There are some dependencies here. All right, so let's take a look at our kinds of translation units table. The last time we saw this, we just had non-modular units here. Now we have added module interface units, which are the ones that have an export module declaration at the front. And they've got the extension .cppm, or there's some other extensions in use. The point is they usually have an extension that's not .cpp. And these generate 2 artifacts when we compile them, BMIs and object files. That has not always been clear throughout the evolution of modules that these generate object files, but in not all cases will they generate an object file that actually has content in it or one that's required. But you should assume that, like in the general case, you should assume that you need to compile your module interface units to an object file and link that into your program. And you have exactly 1 of those per module. And then we have the implementation units where you have up to 1 of those per module, and those are analogous to our source files in pre-C++ 20 compilation. All right, so now let's move on to talking about import. There are actually 3 different forms of import. The first one is just import of a name, and this is like the first class modules import. So this imports a C++ 20 programmatic module, so one of the things that we just saw in the past few slides. The other 2 forms import a header unit, which is a module synthesized from a header. And the reason that header units exist is to provide us with a transition path to allow projects to gradually adopt modules. And we're going to talk a bit more about how they work later. So what is an importable header? So header units, like to use one of these 2 syntaxes, this has to name an importable header. So what are importable headers? In C++ 20, importable headers are most C++ standard library headers, excluding C standard library headers. We'll talk more about why they're excluded later. Potentially some system headers, and headers that you would proclaim importable. But these last 2 bullets here are completely implementation defined. The standard says that the set of importable headers is implementation defined, but it includes the standard library headers. So in the conservative case, it would just be the standard library headers. Today, there's no mechanism for indicating importability, but there is a proposal for a pragma or a attribute to do that, to allow you to annotate in your header, hey, that this is a header that I would like to be either treated as importable or that I would like this header to explicitly not be importable. So let's take a look at some headers that are inherently textual. Assert is the perfect example here because assert, one, doesn't have include guards, and two, it is intended to have different behavior depending on whether or not the in-debug macro is defined when you include it. So the idea is that it doesn't have header guards, so you can include it in one part of your program, and then later you can change whether or not in-debug is defined and include it into a different part of your program within the same translation unit to turn on assertions in just a very specific part of your program. But the problem is that it's inherently textual because the result that you get depends on whether or not this macro is defined, and that macro might change within your program. So we can never make this a modular header. There are some other headers in the C standard library that define macros. When macros cannot come out of the first class modules that we have seen. They can come out of these legacy imports, the imports of header units. So arguably, we could have made these ones importable, but there are some ways in which these macro definitions could be changed by the programmer, so these are sort of inherently textual as well. So we just decided to say we're just going to make the first class C++ standard library headers importable in C++ 20. So if you try to import a header that is not importable, it will be ill-formed, and as we mentioned before, your implementation defines what the set of importable headers are. There's one more important thing to understand here, which is called include translation. And what include translation is when the compiler sees an include, if it's an include of an importable header, your implementation may turn that into an import. So your implementation may take this that you wrote in code and translate it into this and compile your program as if you wrote this. And we will talk about later the implications of this. This is very significant because this is code that you could have written before C++ 20. So if your implementation does do include translation, this may change, in subtle ways, the behavior of your code. Okay, so we've now added one more entry to our kinds of translation units table, which is the header unit here. And these are created when we have an import of braces or quotes. And they're whatever extension you use for headers. I use HPP, so that's the only one I put on the slide. And just like interface units, these get compiled to both a BMI and to an object file. Okay, so I want to reiterate this again. One of the key differences between textual inclusion and modules is that in the textual inclusion model, interfaces, aka headers, are not translation units. They are merely expanded into translation units. In the modular world, interfaces are translation units, which means that they have to be compiled separately. And also, it's important to understand that modules are not translation units. There is not a one-to-one correspondence between a single translation unit and a module. Modules can consist of multiple different translation units. All right, now let's dive into the writing modules part of this talk, the export part of this talk, if you will. So first, let's talk about module names. So module names are dot-separated identifiers. So it's whatever you could have as an identifier, and then you can have as many of those as you'd like, as long as there's a dot between them. So like you can do like boost.spirit, you can do CTRE, you can do blast.level1, but you couldn't do blast.1. The reason is because 1 on its own is not an identifier. That's a numeric literal. So it's not, the set of characters is not the same set of characters as identifiers plus dots. It is like identifier elements separated by dots. The dots in module names have no semantic meaning, but putting on my tooling chair hat, we, as the C++ tool ecosystem, believe that dots will become useful for various different tooling purposes. We believe it's important that we have a syntactic element in module names that is distinct from the set of syntactic elements that are in identifier names. It allows us to give structure to the name of modules. Even if that structure has no actual meaning, that is useful. Okay, so you can only have one module declaration per translation unit. This is true for both module implementation units and for module interface units. So now that we've established that, let's talk about the structure of module units, because the structure of module units is very specific. And the reason that it's very specific is because we wanted to enable fast dependency scanning of modular C++ code. That is, we wanted to make it easy to write a tool that would quickly go through your code base and identify what modules are imported from what source files and what the dependencies of each one of those source files are. And without a very specific structure, that would be complicated. If you could put an import anywhere arbitrarily in your module units, that would really complicate the dependency scanning. We'd have to parse the whole units. So the way we're going to look at this structure, and it's going to expand over time, is the standard says that your module units have to look like this. And what I mean by have to look like this is prior to this, you can't have anything other than comments. And you can't have anything other than comments in between your module declaration and your imports. The ... means anything's fair game. It's just the regular C++ syntax as usual. So as I mentioned, we have two primary types of module units: module interface units, which are the ones that have export in front, and module implementation units, which are the ones that just have the module declaration. I have no idea where my clicker went. We'll figure that out later. So the interface units are analogous to a header, and the implementation units are analogous to a source file, or the source file that contains the definition for some particular header. So let's talk about the export keyword, which is not just used in distinguishing a module interface unit from an implementation unit. It's also used to specify which things are part of a module's exposed interface. So you can export any type of declaration, and I do mean any type of declaration, and there's also a block export form. So you can export function declarations, variables, structs, type aliases, even using declarations. In the block form, everything within the block is going to be exported. You can export templates, although note that the export keyword must go before the template keyword. There, you will have a gut instinctive feeling to want to put it before the type, because that's where you would put it. That's where you usually put specifiers on templates, and that's where you would put it on a regular function. But this is where it goes on a template. And you can also export specific template instantiations. You can export the members of a namespace block. But it's important to note that this does not mean that you're exporting the entire namespace. So in this example here, I've got two namespace blocks, both for namespace foo, and I exported the first one, which contains A, which means that foo A is exported, but the second namespace block is not exported. So anything I declare in that block, if I don't otherwise export it, will not be exported. And of course, because this is C++, we have this lovely syntax, export import, which is called re-exporting, and it's actually quite useful. So what export import says is, I want to import this thing, and then I want to re-expose it as part of my interface too. So like, I've got some dependency that I need to use, but I also want to expose it out to whoever's going to use me. For example, suppose we have a module that exports a template function square, and then we have another module that exports template function add. We're going to call these math.square and math.add. Then we can create a new module which exposes the functionality of both of these modules using re-exports. So this module math here, it imports math.square and then it exports it too. And it does the same thing for math.add. And so the interface of the math module will be, it'll have a square function and an add function. So what happens if we export a function that returns a non-exported type? That's fine. The type can't be spelled in units that import it, but it can still be used. This is called an implicit export. So in this example here, we've got a module A, and it has this struct S. And S is not exported, but foo is an exported function that returns S. So in this code right here, this is fine. Oop, I managed to knock that off. it's fine for us to write auto S0 equals foo because we've never spelled the type S here. But if we try to say S, we'll get a compiler error because this is reachable but not visible. Now, there is a trick that you can use to get this thing. You can't like spell it by name, but you can do this. You can do decal type foo. So you can actually get the thing, but maybe don't do that. So this can be useful, for example, if you've got a function that returns like an unspecified type, like std_bind. Std_bind in the standard is a thing that returns a function object that has a certain semantics, but the type is unspecified. It's an implementation detail. So if you have a type like that in your library and you want to make it a little more difficult for people to actually spell the type because they're not supposed to do it, they're always supposed to call this particular factory function, you can use this for that. It's important to understand the distinction in the modular world between visibility and reachability. So an entity that is visible is something that is in-scoped and can be named. Something that is reachable is something that is in scope but is not necessarily nameable. So in this example here, S is reachable but not visible. Foo is reachable and visible. But because S is reachable, there are still some things we can do with it. We just can't actually name it. All right, so next we're going to talk about how modules provide stronger encapsulation than textual inclusion. We're going to start off with this example here where we've got an implicit dependency between these headers. So we declare a struct foo in a.hpp, and then in b.hpp we use this struct foo. But we don't include a.hpp. We've forgotten to include something that we need here. But in main.cpp we just happen to include a before b. We saw one of these examples before, and if we switch the order of these includes, then it would stop compiling. So this is bad structure. We don't want structure like this. We have a missing dependency here. What we would like is to be able to get a diagnostic about this. We would like the compiler to tell us, you can't do that. I don't know what foo is in the context of B here. So in the modules world, you cannot do this because in the modules world, interfaces are translation units. So the interface, this b.cppm here, this is compiled as a separate translation unit. It's not compiled as part of main.cpp here. It does not have the context of this import here. It doesn't see anything that was imported from A here. This interface is compiled completely in isolation from its use right here. And so you will get a compilation error. This will be ill-formed because in this sandbox where we're compiling this interface, we don't know what foo is. We need to add an import of the module A here. Okay, so let's move on to talk about name encapsulation. Let's say that we've got two headers, each of which defines a template named ID, but they do it in slightly different ways. Like they don't intend for these things to be the same thing. They're just implementing some implementation detail of their library. They both just happened to call it ID. In one of the headers, ID is a function. In the other header, ID is a struct. So because these are templates, these are implementation details, but we need to have them in the header because they're templates. We can't just stick them into the source file. So if we happen to include these two headers in the same translation unit, then we're going to get a compilation error because we have conflicting definitions here. Okay, so you might be thinking, well, this is an easy problem to solve. Don't define things at global scope, right? We should just put these things into namespaces, and then this solves our problem. But the thing is, namespaces do not provide us with true name encapsulation. And also, putting these things into the namespaces, like putting it into the main namespace for our library, might send the wrong message to users. Like it might give the appearance that this thing, which is an implementation detail, is part of our advertised interface. So what we often see in C++ code is detail namespaces, which I absolutely loathe. I'm sure many of you have either written these or seen these somewhere in your code, or seen like an impl namespace. The particular code base I work on has some really egregious cases where there's like detail, like some other namespace name detail, some other namespace name impl. So we do this because we don't want to send the wrong message to users. We want to tell users, please don't use this thing. Don't rely on this. This is our implementation detail. We reserve the right to change it. But as I said earlier, if you ship it in a header, people will use and depend on it no matter what you do. One of the projects I work on at work, it's a header-only library, and we depend on another header-only library that we had just copied into one of our detail namespaces. We'd shipped it with our library, but we'd told people, this other header-only library that's a dependency of ours, you can't use it. You cannot use it. We don't support it. We're just shipping it because we need to use it. Do you think people listened? No. I get bug reports all the time of people complaining because they tried to use this thing that's embedded in like 3 levels of detail namespaces. But I can't stop them today. So what about argument-dependent lookup? Or what about macros? Namespaces do not protect us from either of those things. The reality is that with large libraries that have large user bases, you sort of have to assume, at least for function names, that all names live in a global namespace because of ADL. And in a lot of cases, you have to assume that all names live in a global namespace because people might define macros. Every C++ standard library implementation uses reserved identifiers, as they're allowed to, for all of their all of their names in the library to be resilient to macros. It's really unfortunate that we have to uglify our identifiers and do all these tricks to achieve name encapsulation. In a modular world, we don't have to do this because non-exported entities are reachable but not visible outside of modules, and module interface units and module implementation units are compiled in isolation, and macros can't leak into them. So that we don't have to be adding detail namespaces and implement namespaces in the modular world. We don't have to be uglifying identifiers, and I think that's great. Okay, so one change, or I should say reorganization in C++ 20, is we've sort of shifted around what linkage means. So the thing that used to be known as external linkage is now known as module linkage. This is sort of the linkage that you get for most things, like if you just declare a thing. And the visibility of things with module linkage is within the module that they're declared in. Now, in non-modular units, which is all pre-C++ 20 code, all of these entities have external linkage, which is what we used to call this pre-C++ 20. Anything that is either externed or exported in a module unit has external linkage, which means that it's visible from all translation units, just as it was pre-C++ 20. And internal linkage and no linkage has not changed. But so the default in a module unit is that by default, things are not visible outside of the module. They're only visible outside of the module if you export them. So we finally got one default right in C++. Okay, so now let's talk about encapsulation from macros, encapsulation from macros coming in, and how much encapsulation there is from macros going out. So non-header units never expose macros. This slide is, I believe, wrong. This should say no macros out, and that should say macros out and macros out. So macros can never go in, but they can come out. So let's look at some examples of this. So suppose I've got a macro foo that's defined inside of a module interface unit. So this is not inside of a header that I'm importing as a header unit, but inside of a module interface unit. So if I try to use this macro after I've imported this module, it's not going to work because the definition of foo is not brought in by the import, because I haven't textually included this source code here. I've built this as a separate translation unit, and I've built a interface unit from it, and macros are not exported from module interface units. So this foo definition just does not exist when we import A here. However, an import of a header unit does bring in macros. So when we import a header unit, we will get any macros that it defines. So for example, if this was a a.hpp instead of a module interface unit, but then I imported it as an importable header, I would get the definition of foo here. So modules will never see the definition of programmatic macros defined in other modules. Like we just talked about, they can come out of legacy imports, but they can never go into modules. And by programmatic macros, I mean macros like pound defines. Macros that are defined on the command line, that are defined for your entire translation unit, those will be seen throughout all code in that translation unit. So you can still insert like a build type macro or some sort of version string into modular code by using a non-programmatic macro, so doing it through your build system or on your compiler's command line. So let's look at how this protects modules from malicious macros. So for example, let's say that we've got some module here that's got a struct foo in it, and then before we import it, we try to pound define foo to bar and then undefine it after we've imported it. But this is not going to do anything because importing it does not textually include the interface unit here. So the definition of foo isn't going to be seen in the imported module. Now, this protects us from some malicious stuff, but there's also some cases where it is problematic. There's some non-malicious case examples too. For example, let's say that I wanted to programmatically define debug. I wanted to programmatically request the debug version of some module. Well, this isn't going to work because it's going to depend on what debug was defined to when we compiled this interface unit, not on the definition of debug when we imported it here. So that definition of debug isn't going to be seen by the imported module. So this is also true for imports of legacy headers. So this is a little more significant. If you've got some code today that's a header and you want to treat it as an importable header, that's fine, but it means that you won't be able to programmatically define a macro and have it be seen by that header unit. So programmatic macros are never seen by modules. They are never exported from non-header unit modules. But all in all, I think this is good because it means that with modules, we no longer have to defend names from our users. We don't have to do uglifying of identifiers. We don't have to have detail in impl namespaces. And you might be thinking, Bryce, is that really a thing that happens? Do people really define crazy macros? Well, I got a bug report earlier this year from an open source user. And the bug report was essentially, hey, this large open source library defines this macro warp-any, which is also the name of an identifier within one of the libraries that my team maintains. So this identifier warp-any within our library, it's in a namespace. We've tried to do all the right things, but because we didn't give this some ridiculous name that nobody else would ever possibly think of, like underscore, don't use this warp-any, we happened to run into this conflict. And this bug report was asking us, can you change the name of your thing? We said we did not change the name of this. But this does happen at scale. If you've got a large amount of users, if you've got tens of thousands or hundreds of thousands of users, you will run into this sort of stuff. Okay, so let's talk about some of the implications of modules isolation modules isolation from programmatic macros. So as we talked about earlier, all these standard library modules all the standard library headers are importable headers. So if we want to import vector in this way, and if we wanted to use a programmatic macro to configure our standard library, well, this won't work because this is an import, and as we just established, macros are never seen by imports. So the definition of this libcpp no exceptions, which is the macro in libc++ that disables exceptions, this won't be seen by vector. Now, do you remember earlier where we talked about include translation, where implementations were allowed to take includes of importable headers, like this, and translate it into an import? Well, what that means is that this code, which is code that you could have written pre-C++20, if your implementation does include translation, and they choose to do include translation here, which they can do because vector is specified by the standard to be an importable header, if include translation occurs here, then vector will not see the definition of this macro. This is a breaking behavioral change between C++17 and C++20. Now, include translation used to be mandated. About 6 months ago, it was required that include translation be done here. Now it's implementation defined, which I actually would argue might be worse, because it means on some platforms, which will always do include translation, this will never work, and on other platforms, it'll always work because they don't do include translation. So if you write your code on that other platform where it always works, and then you move to the new platform, you'll be confused why this standard library doesn't see this macro that you tried to define. All right, so how do we deal with non-modular headers? So by that I mean headers that are like inherently textual, like assert, or headers that, like some of the POSIX headers that ask you to define macros before you include them. So we can't import them because these headers are not modular. They're fundamentally textual. So just trying to import cassert will not work. And we could include them, but this is problematic because, as we're going to discuss in a moment, modules own their declarations. And we probably don't want to take ownership of all the symbols in cassert. So what we can do is we can use what's called the module global fragment. So this is an optional part of the module unit structure. If you want to use the module global fragment, you put just the keyword module with no module name after it, and then you can have some number of preprocessor directives. And I literally mean that, just preprocessor directives, no code. You can include things, you can have if-defs there. And anything that's in between the start of the module global fragment and the module declaration, all that stuff will go into what's known as the global module. And the global module is the default owner of all entities that are not modular entities here. So you will avoid having your module take ownership of the declarations that you include. So you would use it like this. So I have start of the global module fragment, then I include my textual headers, then I start my module here. And then this works just fine. You can combine this with exports of using declarations to fairly easily modularize legacy code bases without any changes. Like in particular, if you're not sure if the header that you're trying to modularize is truly importable, you can just do this. You can just do global module fragment and include the thing that you want to wrap into a module. Then you have your module declaration, and then you just use an export using statement to introduce the name and expose it from the module. This can also be useful if you don't want to change the name mangling of the thing that you're trying to wrap into a module. There are two different types of module ownership, and in the strong ownership model, which some implementations plan to do, the mangled name of things that are owned by a module will contain the name of that module. Okay, so the next property of modules are order independent. So import A followed by import B is equivalent to import B followed by import A. I don't have much to say here, other than that, like your implementation could execute the actual imports in whatever order it chooses to. Because they're fully sandboxed, this property just sort of falls out. All right, so modules cannot have cycles. Cycles are strictly forbidden in modules. So we saw this example earlier of a circular inclusion. If we try to write this in a modular world, this will not work for us because, first of all, you cannot have a circular imports in between modules. The compiler will figure out what you're trying to do here, and it'll be like, nope, you can't do this. Still formed. So you might think, okay, I can just delete the imports and just forward declare the things. But you can't do this because, again, these things are compiled in sandboxes, completely encapsulated from each other, so they need the definitions. But you might think, okay, well, it's fine for this to just be an opaque type here. Like, I'm not going to actually use it as anything other than opaque type. But then you run into the problem of ownership. All of the declarations, including forward declarations in a module, are owned by that module. So the problem here is that by declaring Y in this module A tries to have ownership of this symbol. Likewise, here forward declaring X means that this module thinks it has ownership of that symbol. So this is going to be ill-formed NDR to try and compile this. So you can't do this. Unfortunately, it's not, we can't just make it ill-formed. It's difficult to diagnose this because these things are compiled separately in encapsulation. Okay, so the only way to deal with cycles is that you have to break them in your code. There is no good or easy story here. I wish I could tell you that there is. But if we want a brave new world where we do not allow cyclic dependencies, that means that any cyclic dependencies we have to get rid of. So if we have a cyclic dependency like this, where we've got two components, A and B, that depend on each other, and then we've got some other components that depend on each, if they're structured like this, where there's a cyclic dependency between X and Y here, our best bet is going to be to refactor the things that have the dependency cycle into a minimally sized new module like this, and then make the things that depends on anything inside that new module just depend on it. So I don't have any good story here. Breaking cyclic dependencies is difficult to automate. We talked in the tooling study group about some efforts that have been made to try to do this automatically, and the tool was unable to successfully break things up into reasonably sized modules for the code bases it was tried on. But this is good, I think, because cyclic dependencies are a major headache in C++ today. The modular world avoids this headache by disallowing it, but it's going to be painful to migrate to this world. Okay, so we're nearly at the end here. I want to talk briefly about modules owning their declarations. So as I've mentioned a few times, modules own all of the entities that they declare. Ownership means that the entity must be declared and defined in that module here. So as we saw earlier, in a modular world, this means that you cannot forward declare something that lives in another module. Can't forward declare any entity that lives in another module here. So let's look at this example here where we have a function foo that's defined in both a.cpp and in b.cpp. In the textual world, this is going to be ill-formed NDR because we violated the one definition rule. In the modular world, this will just be ill-formed because we can tell in B here that we've tried to redefine something that's owned by another module here. So the modular world will actually catch this ODR violation. So what if we have two declarations of the same entity in different modules, but neither of the declarations are reachable by the others? This is still ill-formed, no diagnostic required, because there's no way for us to tell that we can't even reach the other definition, so we can't see that there's a problem here. So next I want to talk about the flexibility that modules give you in structuring your source code. So modules can be contained in one file. As we discussed a little bit earlier, you can have sort of header-only modules, which are the equivalent of header-only libraries in pre-C++ 20, where you've just got a bunch of templates in your headers. You don't need to have any definitions anywhere because everything's a template. Now, it is important to remember that in the modular world, interfaces are translation units. So in like this that can be just a header that you can just distribute to people as a header in the pre-modular world. In the modular world, the equivalent structure, it does have to be pre-compiled. And in fact, you might also have to compile it to an object file if there's anything in this module interface unit that is not an inline. So modules also have a facility for placing entities that you want to be unreachable into a module interface unit. Think of unreachable as meaning as if they were written in a source file. For example, if you're implementing an opaque struct, which you typically do by you declare it in the header file and then you define the struct in the source file, you can do it the same way in modules where you can declare it in the interface unit and define it in the implementation unit, or you can use what's called the private module fragment, which is a single statement that can appear optionally in your module interface units. It looks like this, module : private. And it means that anything after this is going to be unreachable. So it's as if anything after this was put into a module implementation unit. So this is what the structure looks like of modules looks like with the optional module private fragment. Okay, so now we're going to talk about module partitions, which allow you to expand a module into multiple files. So we looked at this example earlier of re-export where we had two modules and we had a third module that took the interface, or that took the interfaces of these two and exposed it through this new module here. But what if we wanted to only allow the combined interface? So we didn't want to expose math.square and math.add as independent interfaces here. We just wanted people to go through the main math interface here, but we still wanted to keep math.square and math.add in separate source files. So we can do this with module partitions. So module partitions, a module partition is any module that has a colon in the name here, and the things before the colon is the name of the parent module. The stuff after the colon is the name of the child module. Module partitions are, you can think of them as private submodules. They belong to some parent module. Only the parent module and other partitions of that same parent, so its siblings, can use the exported interfaces of the partition, and you can't import a module partition outside of the module that it's a part of. The parent module can re-export module partitions or entities from its partitions here, which is what we're doing right here. So this the main module interface file re-exports both of these, but you can't, if you're not in this module, you can't go and import math semicolon square here. So we're going to look at our last example, which is a little bit more complicated here. So we've got a main module interface unit, math.vector, and it re-exports the interface of one of its partitions, dot product. It also has a declaration of a square root function which is not exported. So that just means that it's going to be used internally by some of the module partitions. Then we've got our dot product partition here, which is just going to be an interface unit, and it imports another one of the partitions called sum squares, and it imports it because it's going to use this function sum squares, which is going to be defined in that other partition. It also uses square root, which is declared by the primary module interface unit. So then we've got our sum squares partition here, and it exports that sum squares function, which is used in this partition over here. Now notice both this vector norm is exported and this sum squares is exported by these partitions, but only vector norm will be exported by the module math.vector because this module interface unit did not re-export sum squares. So sum squares is an internal only module interface. And then finally we have the implementation unit for math.vector, which defines the square root function here. Now, module partitions can have their own implementation units, but in the interest of brevity, I have not included that in this example. So this is the final form of our kinds of translation units table. There are now 6 types of translation units in C++20, although partition interface units and partition implementation units are essentially just a subset of interface units and implementation units. The important takeaway here is that modules don't force a particular file layout on you. With module private fragments and module partitions, you have a great deal of control over how you structure your modules. You can compress a module into a single file, or you can spread one across multiple files with implementation units and partitions. And as I mentioned earlier, modules are not translation units, as we just saw. That math.vector module, there were 4 different translation units involved there. One primary implementation unit, 1 primary interface unit, and then 2 partition interface units. But they were all part of one module. So we started this talk by discussing all the problems with the textual inclusion model. Modules solves or greatly reduces all of these problems. So modules will bring us substantial algorithmic build throughput improvements. You no longer have to compile your interfaces in every translation unit that uses them. Modules also, and more importantly, offer us true encapsulation, which makes it easier to write C++ at scale. But transitioning to modules will not be free. And unfortunately, I'm out of time, so I'm going to stop it here. But the C++ committee's tooling study group is working with tooling vendors and implementers on a C++ modules tooling interactions technical report, which will probably come out sometime between a year from now and 2 years from now. And that technical report will be sort of an auxiliary document to the main international standard that will describe many of the ecosystem components of modules that aren't suitable for the main standard. So for example, there will be some formats in that technical report for things like dependency metadata, package manifests, and module recipes, which is sort of the instructions on how do you rebuild a particular BMI. And thank you all for your time. If you've got questions, come and find me later.